do admit everyone.
Yeah, okay.
Ask them to join through live.
Live?
Put on in text messages in QGB link.
KGB?
Yeah,
Okay.
I think it's live. Welcome to Physics Clinic, my dear children. Today's topic is actually atoms and nuclei. We are going to see. This is class 12 portion. Since it's a crucial time for class 12 children, you are having your pre-board exams or a kind of annual exam. It's going to happen. So do stay with me for learning, easy learning. Okay. So today's topic is atoms. We are going to see. So all this history, it is connected with atomic structure, what you have learned in class 11, right?
Yes, ma'am.
Class 11, atomic structure in chemistry. Okay. In the last lesson, I have taken dual nature of matter. What is the dual nature of matter? That is also associated with that particular chapter. If you break the chapter, structure of atom of class 11 chemistry, so I'm just insisting always, you should keep your 11th book and then 12th book also, so that it is easy for you to write your JEE mains exam. Is it visible clearly?
Yes.
Is it okay?
Yes.
Okay. So then, what I'm trying to say, you should definitely have your class 11 book also with you. Okay. So in a class 11 structure of atoms, you will be having all the histories and discoveries, right, of atomic structure, starting from J.J. Thomson to Bohr's postulates, and then Einstein's, and then I think Planck also, Planck's theory also discussed in that. Bohr's, de Broglie wavelength also discussed in that. Dual nature. Okay, and then photoelectric emission also discussed in that particular chapter. Okay, so in physics class 12, what they did, they have just segregated all these things. Like in the dual nature, you will be given all about photoelectric emission and how de Broglie came into that conclusion that each and every particle exhibits in the waveform also. Okay, so that is all discussed over here. Okay, especially mainly. What is that? Photoelectric emission. Full chapter is all about photoelectric emission.
Yes, ma'am.
Okay, that dual nature, it comprises only, it talks about dual nature, but even then, initially, what is the experiment performed?
Okay.
Photoelectric emission. Based on that only, all these conservations, all these observations, okay, they did. So then what is the next one? Next topic is atoms. We are now going to look around atoms. You know all these things, right? Rutherford. So all the history everyone knows. Understood or not?
Yes, ma'am.
Okay, Goldstein, he performed an experiment. Okay, first Rutherford's experiment is alpha particle scattering. Okay, go through this, and very important for your JEE mains also. JEE mains, you will be having extra syllabus like experimental physics, right? In experimental physics, they have included all the experiments what are all discussed in the NCERT syllabus itself, not from the deleted portion. So this and all, these experiments and then discovery are included in that. Okay. Yesterday we saw photoelectric emission, that is also included in that. A photoelectric emission also performed by an experiment, that is included in that.
Ma'am, இந்த பாட்டு ஏதாவது question இருக்கா ma'am? அந்த alpha particle scattering
Yeah, definitely you will be getting questions. For example, like reason assertion questions it will be. What are all the what are all the benefits from that? So what are all the what are all the drawbacks from that particular discoveries? Okay, so that drawback can be rectified by the next scientist. Okay, like for example, Einstein also considered first the atomic orbit as a circular orbit. Then Sommerfeld came and he only just suggested that if it is in circular orbit, definitely it doesn't suffer a proper or constant angular momentum. Okay, so it resembles like our solar system. So here also electron are revolving around the nucleus in an elliptical orbit. He justified in such a way that you might have studied in your higher classes, after class 12. Okay, but this is what I am saying. All the theories or postulates discovered by the scientist, there are some drawbacks and failures that will be rectified by the second scientist, like a way. So you have to go through all the theories and take a note of all these things. Children, what you are going to do? You have to write the name of the discovery. For example, if you are writing alpha particle scattering, I will explain you how you are going to take a notes. Okay. So here it is given alpha particle scattering and Rutherford's nuclear model of an atom. See, for example, you can write a note of all these here also. Okay. So what is this here? 1911. Right. So Geiger and Marsden performed some experiments. In one of their experiments shown in this figure 12.1, they directed a beam of 5.5 million electron volt. So stay along with me and take a note. Okay. Write a note in 1911. Okay. Who are all the scientists involved in that? Rutherford, Geiger and Marsden. This Geiger is Geiger-Müller only. Okay. Then you have to admit what is this beam? This beam is nothing but they directed a beam of 5.5 million electron volt alpha particles emitted from a bismuth radioactive source. So this is you are going to learn what is actually the radioactive elements, what is alpha particle, what is beta particle and everything. Okay, alpha particle is usually the helium atoms. What is the helium atom? What is the valency of helium atom? What is the valency of helium atom?
Plus 2.
Okay, so how you can see? How many number of electrons in it?
2 electrons.
Okay, so what is the mass number?
4.
So what is the number of protons? Neutrons?
2.
2 neutrons. Okay, this is the basic thing. It consists of 2 electrons and 2 protons. Okay, suppose if the helium loses its electron, for example, okay, it may lose 2 electrons. Understood? So what will be the remaining? Ig2 plus.
Yes.
So it is said to be a perfect alpha particle. Understood or not?
Yes.
So if some electron is emitted, that is known as beta particle. So beta particle is nothing but electron. Electron is said to be a beta particle. If the electron is emitted after the bombardment of actually the nucleus. We are now going to see how the nucleus gets bombarded by some other atom and then what all emitted from the nuclear radiation as a nuclear radiation. So as a nuclear radiation, helium may be emitted. So this is the experiment carried forward here. So helium is an alpha particle. Understood?
Yes.
Then there is gamma particle also. It is highly radiated one and then it is very harmful also. Okay. So these and all we said to be this is atomic explosion or nuclear explosion like. Okay. So I will be coming to this. So what is it actually? It is a gold foil. It is acting as a metal target.
Yes.
Okay. Then what will happen? This figure 12.2. Where is 12.2? Okay. This is next. Okay. So bismuth. Okay. 5.5 million electron volt alpha particles emitted from a bismuth radioactive source. So bismuth, uranium, then thorium, these are all radioactive isotope. So radioactive means, what is the meaning of radioactive? If its nucleus gets bombarded by, since you are not having any nucleus lesson in your 9th and 10th, 11th also, so now only you are going to learn. So you must understand the nucleus gets bombarded. Okay, so bombarded means it gets collapsed. Okay, by some external source. Any light source also can be taken.
Yes.
So light may be incident on it, for example. then what will happen? The nucleus gets collapsed and then it broken into pieces. Like if that is uranium, uranium is broken into two more compounds. Since uranium is highly isotope, so uranium is definitely we'll come into that reaction in nuclear fission and fusion.
ಮತ್ತೆ elements ಎಲ್ಲ அப்படி ஆகாது நியூக்ளியஸ் ரெண்டா
Yeah, no. Nuclear level bombardment doesn't happen. Okay, only for radioactive isotopes. So that it is said to be radioactive. Okay, radioactive means it is ready to emit such a radiation.
yes
Understood? Okay, so first of all, you can understand from this part. Are you all writing? You better write. This is the source, radioactive source. Bismuth. You can write along with it 214-83. 214 and 83. Okay, so what is this? 83 is the atomic number, 214 is the mass number. See how high it is. So what is the number of neutron here? Make it fast. What is the number of neutron?
120
120?
1 neutrons
121 neutrons, right?
Yes.
So number of neutrons are very high, so that it is ready to radioactive. It is ready to promote, or we can say it is ready to radiate energy. Okay.
நியூட்ரான் அதிகம்
Neutron is coming out from the nucleus. If the nucleus gets collapsed, then what will happen? The neutrons gets coming out.
ஓகே
It may emit 1 neutron or 2 neutron. Okay, if 1 neutron is emitted, then that is very high actually. How the electron is lost by an atom by means of ionization energy. How an electron is gained by an atom by means of electron gain enthalpy.
yes
So each and everything energy is required for an atom. Understood?
yes
If the atomic bombardment takes place in nucleus, it needs as much of energy. When it is once get bombarded, then that much of amount of energy is radiated out of it. Both of you learn? Learn. Okay, so that is what it says actually. So if 1 neutron is emitted from a nucleus, then that brings out that much of energy. Okay, so that means, for example, if alpha particle is emitted from it, that is helium-2 plus is emitted from it. If alpha particle is emitted from it, how much of energy is there? 5.5 million electron volt. It is not micro, it is million. Million means, what is million? 1 million.
10 lakhs
So 10 per 6, right? 10 lakhs means 10 per 6.
10 power 7
So 10 per 6 electron
10
volt.
power 6 1 lakh
10 per 5 than 1 lakh.
10
1 lakh into 5 zeros. Okay. So 10 per 6 electron volt is 1 million.
yes
So 1 million electron volt is, 5.5 million electron volt of energy, alpha particles emitted from a bismuth radioactive. Okay, at a thin metal foil made of gold. So from this one experiment, so how much of energy is emitted? See, it's a very useful experiment they did on those days. Okay, then this figure 12.2 it shows schematically. See, it is a schematic expressions. What is here? What is it? Lead bricks. Why lead bricks are there? Because it is very harmful. I said no. It is protected by a wall or lead bricks. Bricks made up of lead. Okay. Since lead is not reacted with the particular alpha particles, it is not non-reactive with the alpha particles. So lead is needed there. Pb, lumber. Okay. So they are using this lead bricks, and then what will happen? The source of alpha particles here. There are thin gold films up here, right, Ma?
yes
Okay. So how the alpha particles scattering over here, it is experimented by the schematic diagram. Okay. See here the scattering of alpha particles you might have seen. So the alpha particle is coming through this thin gold film. This is thin gold film. Okay. So through this, part of the alpha rays are slightly scattered. small angle of scattering, and then part of the alpha rays are like this with an angle theta. Okay, it is detected by a microscope. This is actually zinc screen, okay, zinc sulfide screen.
Okay.
Then what will happen? Backward scattering also takes place. A very small fraction. That means if 8,000 alpha particles scattered in this direction, then one will scatter in the backward direction. Okay?
Okay.
Like it is given, so it is expressed over here. Then make a note of this. So what is given here? Next one, the beam was allowed to fall on a thin film foil of gold of thickness 2.1 into 10 power minus 7 meter. So what is that? You can imagine how much small it is. Okay? So 2.1 into 10 power minus 7 meter means, so we can write 2.1 into 10 power minus 4 millimeter. Right? What is that? 0.00021 millimeter. Okay? Or we can say it might be in micrometer, 0.2 micrometer. It's very, very small thickness, the gold thickness will be.
Yes.
Okay, that gold foil is kept. Okay, and now the scattered alpha particles are observed. Okay, by means of this gold particle, all the alpha particles are scattered. Understood?
Yes.
Why it is so? Maximum gold is a metal. Okay, metal has the ability to.
Lose electrons.
That means it might be a cation, right?
Ah.
Alpha particle also a positively charged particle.
Yes.
Okay, it gets scattered. It may be deviated from that particular gold foil. That is why they have
அந்த
this instant.
நியூக்ளியஸ்ல புரோட்டான் இருக்கறனால அது பாசிட்டிவ் சார்ஜ் ஹீலியம் 2 plus பாசிட்டிவ் சார்ஜ் அதனால இருக்கு.
Both gets repelled. Okay,
Yes.
both are like charges, right?
Yes.
Is it clear for you? Then what they said, you just write everything here, okay? So this is a rotatable detector. So this detector can be rotated along with the zinc sulfide screen. Detector sometimes may be here, sometimes here, so that it can be detect all the rays which is scattered.
Yes.
Get my point? Understood?
Yes.
You had to write all the scattered rays. What are the types of scattered rays? The small angle scattering of some rays will be there. Then with large angle also there. Then backward scattering also takes place in a fraction. That is 1 in 8,000. Okay? Understood?
Yes.
So the scattered alpha particles on the side of the screen produce brief light flashes or scintillations. Like a light flash it gives. Okay? These flashes may be viewed through a microscope, and the distribution of number of scattered particles may be studied as a function of angle of scattering. This is an angle of scattering. Okay? So by means of the flash only we can able to understand the helium particle is emitted. Scattered.
Yes.
Okay, so by means of that we can able to find the amount of scattering as well as the angle of scattering and everything. Okay. So from this experiment you will be asked questions like this. Okay. So backward scattering is not possible, like in an assertion it will be given.
11th வந்து பேக்வர்ட் ஸ்கேட்டரிங் வந்து 1 in 18,000 அப்படினு வெச்சிருக்காங்க. சோ அது இம்பாசிபிள் சொல்றாங்க.
1 in 8,000.
18,000. 180 degree scattering.
No. What I am trying to say, 1 in 8,000 means what does 8,000 represent? Number of alpha particles.
Yes.
Out of 8,000 alpha particles,
11th சொல்றேன். 11th வந்து இதே கேஸ் தான் வந்துச்சு. ஆனா மேக்ஸिमम வந்து அந்த கோல்ட் ஃபாயில பாஸ் பண்ணி போயிடும். ஆனா சம் பார்ட்டிகல்ஸ் வந்து டிஃப்ளெக்ட் ஆகும். அதுல வந்து 1 in 18,000 வந்து full 180 degree scatter ஆகும்.
அது 180 degree ல. Okay, this is not 180 degree, right? Okay?
Okay.
Understood?
Yes.
180 degree வரும்போது you might understand definitely 1 in 18,000. Okay, it is very rare.
Okay.
Okay, it is also rare, but it is very rare.
Yes.
Okay. So we just go through it. A typical graph of the total number of alpha particles scattered at different angles in a given interval of time is shown in the figure. Okay. So here, scattering angle, for each and every scattering angle, how many number of scattered particles detected? See here, okay, this graph clearly pictures everything. Okay, so Geiger and Marsden, they just observe all the experimental data and then they drew this graph. Understood?
Yes.
So like we just go through it and then write a point. It's all about theory. Understood? See, they said like class 11, yeah, everything it is given. We'll discuss about this. In Rutherford's nuclear model of the atom, the entire positive charge and most of the mass of the atom are concentrated in the nucleus. You know, right? What is that? What is the center of mass for an atom? Nucleus.
Nucleus.
Most of the mass, 99% of the mass is concentrated in the nucleus. Okay. So, with the electrons some distance away, the electrons will be moving in orbits about the nucleus just as the planets. These are all you know. Okay, size of the nucleus is about 10. This also you know, right? 10 power minus 15 meter to 10 power minus 14 meter. Atom size will be 10 power minus 10 meter, right?
Yes.
Okay. Then, how much atomic size is bigger? Why it says from kinetic theory? Because each and every electron revolves around the nucleus in various orbit, right?
Yes.
If the electron is in motion, then definitely kinetic energy is associated with that. So based on the energy only you can able to assume what is the first energy shell, what is the second energy shell, right? Clear?
Yes.
So how much it is bigger? 10 power minus 14 and minus 15 to minus 10 means 10 power 4 times it is bigger. 10 power 4 times or 10 power 5 times it is bigger. Understood?
Yes.
So, okay. Then the electrons would seem to be at a distance from the nucleus of about, okay, again and again the same point is insisted. You can go through it and write a point. Okay? So this is very important. As the gold foil is very thin, it can be assumed that alpha particles will suffer not more than one scattering during their passage through it. What is the meaning of this? Huh? From the data shown in the figure. What is the data shown in the figure? What they said, since the foil is very thin, what they said here, what is the statement they have given here? As the gold foil is very thin, it can be assumed that alpha particles will suffer not more than one scattering. So that means one alpha particle suffer one scattering. Like the way they are addressed here.
Yes.
Understood? So during their passage through it. Okay? It uses, the gold, since it is very thin gold film, right? It is very easy for the alpha particle to scatter from it. So it doesn't suffer repeated scattering. For example, if it is very thick, then what will happen?
நிறைய atoms pass பண்ணி போறீங்க.
Yeah, it has to travel. The alpha particle has to travel much distance and then it is scattering right now, like this, right? Understood or not?
Yes.
Since it is very thin, it is very easy for that particular one alpha particle, if you are considering, to scatter easily. Right? Understood or not?
Yes.
If it is highly thick, definitely so many backward scattering takes place
Yes.
instead of forward. Okay? So that's what they are trying to explain here. Okay? So underline this point and then you have to write this point. This will be asked in your MCQs. Okay? Therefore, computation of the trajectory of an alpha particle scattered by a single nucleus is enough. Okay? See, for example, what they are trying to say, if you are taking a quanta of material, you will not say there is one alpha particle. Right?
Yes.
Okay. But here, we can consider one alpha particle or one nucleus. Okay? So, for observation. Then alpha particles are nuclei of helium atoms, right? Just now I am saying, right? What is alpha particle?
Helium 2+.
Why it says nuclei of helium particles? Because helium has a tendency to lose 2 electrons. So that it is having only nucleus in it.
Helium noble gas
Understood. But we can make it. We can just remove 2 electrons from it. That can be artificially done.
But why not hydrogen? Hydrogen can use hydrogen.
Hydrogen is universal element. It is easy, right? It is easy to give any type of body. So why we are just doing all these things?
Helium
Hydrogen doesn't have nucleus, neutron. You are asking that, right? Hydrogen doesn't have neutron.
Okay.
Helium is having the neutron.
Proton experiment.
Neutron only we are talking about now. Neutron emitter. Okay, actually, here they are saying, here they are detecting the alpha particle trace. They are tracing, they are just adding up the trajectory of the alpha particle. How the alpha particle is.
Okay.
They are just learning. Based on that, you are now going to learn about all nuclear fission and fusion.
Okay.
Now, then only you can get a clear idea. Okay, so now the experiment is carried out for understanding how the alpha particle is deflected.
In the experiment, neutron.
No, actually, what I am trying to say, then only they came to know about neutron also emitting. Neutron also emitted in the process of bombardment. If it is bring, see where the nucleus is coming. Only one part is discussed over here. Right, Darshan? Only this part is discussed. Right, alpha particles, source of alpha. Where the alpha particles are coming? There is one process behind. That is what I have explained you.
Yes, ma'am.
Initially, this is radioactive process. Actually, here nuclear fission takes place. Understood, ma'am?
Yes, ma'am.
Bismuth is undergoing this. From there, you will be getting neutron and helium nucleus. See, for example, helium particle is basically, right now it loses its electron and then it is having only nuclei. Okay?
Okay.
Is it clear for you, ma'am?
Yes, ma'am.
Take a note of all these things. This will be asked in your test. Then, alpha particles, okay, what I said. Just now I told what is helium atoms, but in your book here only it is given alpha particles are helium atoms. Initially it's not given. I've explained you everything. Okay, don't take it easily. You have to take everything in your account. Okay, so you take a note. What is this? Therefore, carry 2 units, 2 electron of positive charge and have the mass of helium atom. Okay. So the charge of the gold nucleus is Z into E, where Z is the atomic number of the atom. You are denoting with that letter, right? Atomic number of the atom. For gold, what is the atomic number now? 79. E is the charge of an electron or proton. What is the charge of an electron or proton?
1.6
10 power minus 19 coulombs, right?
Yes.
So it is reasonable to assume that it remains stationary throughout the scattering process. Which one? Nucleus of gold. So the gold nucleuses remain stationary. Understood or not?
Yes, ma'am. Understood.
Why it is remaining stationary? Since it contains 79. The atomic number is 79. What is its valency?
Gold, ma'am.
The atomic number is 79. So take it as an assignment. Still you are in 7th standard or 8th standard. How do you find the valency? You just think it about. Like a way, one sentence, it comprises lot of linkage. It links to some more topics. Okay. So think about the valency. Definitely the valency of a metal will be either 1 or 2 or 3 maximum. Understood? If it is 1, for example, you can understand. Suppose if the gold is emitting 1 electron, then remaining 78 electrons will be there, which act as a gold cation. Understood or not?
Yes, ma'am.
Gold ion. That is said to be the nucleus of a gold. Totally. I told you, no, the positive charge means the total cation is a positive charge. Lighter way. So that it remains stable. Even though alpha particle is coming, okay, it won't mix up with or it won't get disturbed by the alpha particle. Since alpha particle is containing less number of neutrons and protons. Understood?
Yes.
So when compared to one, they are just comparing one gold atom and one alpha particle, helium atom. What an atom we are saying, one gold ion and one helium ion.
மேம் இல்லைன்னா இப்படி சொல்லலாம்
Yeah.
ஹீலியம்ல 2 புரோட்டான் தான் இருக்கும் இதுல மேக்ஸிமம் நம்பர் ஆஃப் புரோட்டான்ஸ் இருக்கறனால டிஃப்ளெக்ஷன்ஸ் ஐ மீன்
Very
ரொம்ப
high.
ரிப்பல்ஷன் அதிகமா இருக்கும்
Yeah, it easily deflected alpha particle. Alpha particle is very lighter. So this is the ratio between 1 to 1 atom.
ஓகே
Then we can just extend that property to whole, right?
எஸ் மேம்
So for since the nucleus of gold is about 50 times heavier than an alpha particle, right? They are same. Okay? You have to determine like this, Z into E, right? What is Z? 79 times 1.6 into 10 to the power of minus 19 coulomb. What is the Ze for helium? This is for gold. For helium, it will be 2 times 1.6. If you divide this, 80 by 2 will be 40. They are saying nearly 50 times.
எஸ்
Okay, 50 times heavier than an alpha particle. It is reasonable to assume that it remains stationary throughout the scattering process.
எஸ்
That's why it is remained stationary throughout the scattering process. This will be asked as a question. Why it remains stationary? Why the gold particles remain stationary? It will be a question for you. Okay, take a note of this question. From here, you will be given question like the nucleus of gold dust remains stationary throughout the process than an alpha particle. Why? What is the reason? Nucleus of gold is about 50 times heavier than an alpha particle. You can comparatively measure, okay, by means of this Z times V. Z is atomic number. So next, we'll move on to, okay, it is reasonable to assume that it remains stationary throughout the scattering process. Okay. So under these assumptions, the trajectory of an alpha particle can be computed employing Newton's second law of motion. What it is given under these assumptions, the trajectory of an alpha particle can be computed employing Newton's second law of motion. Why here the trajectory of an alpha particle can be computed employing Newton's second law of motion and the Coulomb's law also for electrostatic force of repulsion between the alpha particle and the positive charge nucleus. This at all I have already explained why the alpha particle is scattering, why it is deflected back
எஸ் மேம்
due to
பாசிட்டிவ் சார்ஜ் ரிப்பல்ஷன்
both are positive charge, so that force of repulsion must be there.
எஸ்
That is an electrostatic force of repulsion, or you can say light charges repel each other.
எஸ்
Is it clear for you?
Yes.
So that is all here explained. Why they are using second law of motion, mark? Let me know. Make it fast. Why they have insisted here second law of motion also? Hello. Second law of motion deals with what? Force.
எஸ் மேம் ஃபோர்ஸ்
Right. So second law of motion deals with force. Since why here force is there, so the trajectory of an alpha particle can be computed. What is the meaning trajectory of an alpha particle? Alpha particle is moving right now. It is deflecting towards each and every directions. It is moving. If it is moving, definitely it is associated with force, some driving force. Okay. So that force that clicks in the mind of those scientists. You have to think everything in scientist perception. Okay. So this clicks in their mind. Since it is moving, right? Nobody is there to drive. We are not helping them, right? It is moving automatically. So it is experiencing some force. What force it might be? Definitely Coulombic force. That Coulombic force might be definitely repulsive. Okay. So how it might be repulsive?
Ma'am, in the
Both are like charges.
Yes.
Okay. So what is the Coulombic force? Everyone learned from the first lesson.
F equals to K Q1 Q2 by R square.
Yeah, the same thing they have explained here. Okay, what is the magnitude of this force? F is equal to, instead of K 1 by 4 pi epsilon naught, what is Q1 Q2? Q1 is helium particle.
Again Z.
Q2S.
Again Z ன்னு போட்டுருக்கு.
Z can be 79.
Ah,
You can replace it.
Yes,
No problem. Okay. So 2E into Z. See, for example, instead of gold, some silver can also be used.
yes.
For example. So that they have just generalized like Z into E.
Okay.
Okay. That is, it's an advisable amount of atomic number. Okay. Understood, ma? Understood or not? Or
Yes,
should? Okay. So where all is the distance between the alpha particle, you just better admit who are all attending. Okay, this is all you know, right? Yeah, that's all. So alpha particle trajectory is shown here. This is the targeted nucleus. Alpha particle are coming and then deflected like scattered. See this picture, it shows clearly what it is happening. It's deflected like through an angle, theta. Okay? So for example, a given team of alpha particles has a distribution of impact parameters B. What is an impact parameters? This is how the alpha particles are distributed within this thickness they are saying. As we discussed about a beam, beam means definitely it should have some thickness. We can talk about in that.
Okay.
Okay, so they are saying this B is a parameter, impact parameter, that is the alpha particle beam is within. Then so that the beam is scattered in various directions with different probabilities, right? We don't know why they are saying probability. We can find this alpha particle after collision, or we can say after deflection, it is now here. The probability of finding an alpha particle is different. Different for different places,
அதாவது
right?
அந்த ஆல்பா பார்ட்டிகல் அந்த பீமோட எந்த பார்ட்ல இருந்து வரலாங்க?
No, not like that. The beam is coming in same way. See here, you may find a group of alpha particles. Millions or trillions of alpha particles, for example. See, for example, here you are considering 4 alpha particles. You are looking at it.
Okay.
Within this B parameter, you can watch it over this alpha particle. After hitting this target nuclei, then what will happen? This target nuclei, you will find the first alpha particle here,
Yes, ma'am.
the second alpha particle here, third alpha, likewise. Each and every alpha particle has its own direction. It is deflected. It is randomly deflected.
Okay.
So some angle it is forming, some angle theta it is forming. So they are saying different probabilities are existing in that. Okay? Understood?
A beam of alpha particles na
Yeah,
or group
this is
of
also very, yeah, beam means a group.
Yes.
A group of alpha particles. This is very important. Make a note of it. In a beam, all particles have nearly same kinetic energy. That is very important. All alpha particles, why it is all alpha particles having same kinetic energy? Since it contains, each and every alpha particle contains two electrons, 2 protons and 2 neutrons.
Okay.
Definitely everything suffers same kinetic energy, half mv square.
மேம் ஆனா அந்த நியூக்ளியஸ்க்கு எவ்வளவு க்ளோஸா போகுதுங்கறத பொறுத்து அந்த கினெடிக் எனர்ஜி மாறும்.
No.
மேம் டிஃப்ளெக்ட் ஆகும்போது கொஞ்சம் இம்பாக்ட் அதிகமா இருக்கும் ரொம்ப க்ளோஸா இருந்தா.
No, they are talking about the beam. The beam here. So all the particles have nearly same kinetic energy when you take it as a beam. Okay? Small impact parameter means that is the beam. In your book, the word is given small impact parameter. That is this B. Within this, it suffers equal kinetic energy. Okay? Then what will happen? It suffers large scattering. In case of head-on collision, the impact parameter is minimum and the alpha particle rebounds back. For a large impact parameter, the alpha particle goes nearly undeviated and has a small deflection. What they said, see for example, here if you look at it, this is the parameter, the small parameter, right? Clear?
Yes, ma'am.
If the parameter is very small, it gets deviated by an angle, for example. Okay, see backward deflection also happening. If the parameter is high, then it may experience less deviation. See, the angle is very less. Understood or not?
Yes, ma'am.
It is very less when compared to this. Okay, that is what they are explaining here. If the parameter, if it suffers large scattering, then the small parameter will be there. Impact parameter. It is known as impact parameter.
Yes, ma'am.
Okay. If it is large impact parameter, then it has small deflection. Okay. So the fact that only a small fraction of the number of incident particles rebound back indicates that the number of alpha particles undergoing head-on collision is very small. So when it is head-on collide, then it rebounds back. Okay.
Yes.
So only very small can suffer that kind of collision. Okay. That's all. True the force scattering therefore is a powerful way to determine upper limit to the size of the nucleus. From this we can able to find the size of the nucleus also. How much density of the alpha particle is scattering. So this way we can able to find the nucleus size of the nucleus. Okay. So you better go through all the examples. If you are not getting anything, let me know, I will explain. See, based on this, definitely you will be getting one problem.
Okay.
Very easy only. Then electron orbits we discuss about here. So, we'll discuss shortly.